Okay, so we're going to finish up this section by looking at the fundamental theorem of curls, which is better known as Stokes Theorem. Essentially what this says is we can determine the total twist over some surface, which is given as the integral of the curl of our vector over that surface is equal to the total twist around the outside. And that's given by the dot product of our vector with the infinitesimal displacement vector integrated around that path. Okay, so here in the above equation, dA is our infinitesimal area element and dl is our infinitesimal displacement vector. So we're going to do an example. And we're going to test Dokes theorem for the above function. And we're going to do this using the triangular shaded area shown in that figure. So first of all, what we must do is determine the curl of the vector v. Okay, so this is going to be equal to, so we take the derivative of the z component with respect to y, is 0, minus derivative of the y component with respect to z, x hat, plus the derivative of the x component with respect to z, minus the derivative of the z component with respect to x, y hat, plus the derivative of the y component with respect to x, minus the derivative of the x component with respect to y, z hat. So just write this a little bit neater. We have minus 2y x hat minus 3z y hat minus x z hat. Okay, now what's our infinitesimal surface area element, dA? Well, we can see that both y and z are changing, whereas x is constant. So the infinitesimal surface area element is dy, dz in the x hat direction. So now what we must do is integrate the dot product of the curl of our vector and the infinitesimal surface area element over that surface with respect to dy and dz. So we've got a double integral of minus 2y dy dz. Okay, now remember x hat dot x hat is equal to 1, x hat dot y hat is equal to 0. So this is how we obtain minus 2y dy dz. Now what are integration limits? Well, for y goes from 0 to 2 minus z, and z goes from 0 to 2. Okay, so when z is equal to 0, y is equal to 2. When z is equal to 2, y is equal to 0. Okay, so here we go, we have 0 to 2 and 0 to 2 minus z. Okay, so let's do the integration with respect to y first of all. So what we are going to get is minus, which I'm going to put into the outside. We're going to get, we have 2y squared over 2. So now we've got y squared, and we substitute for y. So you have 2 minus z to be squared dz. And then we'll integrate with respect to z, and what we're going to get is 4z minus 2z squared minus z cubed all over 3 between 0 and 2. And we see that if we substitute in for our z, we're going to have 8 minus 2 cubed over 3. So what we get here is minus 8 over 3. Okay, so that's our first answer. Now what we're going to do is we must work out what the integral around the path is of v dot dl. Okay, so first of all, what does v dot dl give us? So if we consider that dl is equal to dx x hat plus dy y hat plus dz z hat, v dot dl is going to be equal to xy dx plus 2yz dy plus 3zx dz. Okay, so we have it's equal to x, y, dx is the first one, plus 2y, z, dy, and finally plus 3z, x, dz. Okay, so that's v dot dl. Now we have to consider three paths here. The first path that we're going to take is going to go from the origin out to y is equal to 2, so this is our first one. The second path is going to be back from the y to the z axis, that's the second path, and the third will go from z is equal to 2 to z is equal to 0. Okay, so one thing we do know for the surface is x is going to be equal to 0. Okay, since x is equal to 0, dl is going to become now 2yz dy. Okay, that's along each line. Okay, so the first path, x equals to 0, z is equal to 0, dx equals dz, which is equal to 0. Okay, so dl is equal to dy y hat. Okay, so then we do v dot dl. What we get is 2yz dy, which is equal to 0, since z is equal to 0. Okay, so now let's look at the second side. Okay, so again we have x is equal to 0. Y is going to go from 2 to 0. And z is equal to 2 minus y. Okay, so when y is equal to 0, z is equal to 2. When y is equal to 2, z is equal to 0. Okay, so again we have the x is equal to 0. dz is equal to minus dy. So what is v dot dl here? So our integral of v dot dl for this side is going to be equal to 2y into 2 minus y dy. And the limits are from 2 to 0. So now if we integrate this, I'm going to reverse the limits and put a minus on the outside. We are going to get 2y squared minus 2 over 3 y cubed, and that's from 0 to 2. So this is going to give us 2, 4, 16, minus 8 over 3. So now for the third side. Well, for the third side, we have x is equal to y is equal to 0. Z now goes from 2 to 0. And our integral of v dot dl is going to be equal to 0. Okay, so it's equal to 0, of course, because y is equal to 0. So now we just have to sum these up. And what we see is we have 0 plus minus 8 over 3 plus 0 is going to give us an answer of minus 8 over 3. And hence, Stokes' theorem has been verified since we get a similar answer over here.